six questions, and just one problem, and others all are theory. One problem, which is question number 4, as usual, guys. So try to answer your tutorial first. I'll give you some time, and then I'll show you the answer, and then we discuss there after that. Okay, and then while you're doing, try not to refer at the notes. Try to think of yourself and answer by the logical sequence that you have studied so far. Then if you can't answer, let me discuss with you, then you can look at the slide notes. Okay, so that by doing this you can effectively learn something today. Okay, now look at question number 1. Provide 3 types of strengthening mechanism in metals. So strengthening mechanisms of metal, you can find the answer. Try to recall back lecture 3. Okay, try to recall back lecture 3. So I'm giving you some time now. Try to answer this, guys. It's pretty straightforward. Maybe you can answer question number 2 as well. It's pretty straightforward for question number 1. For question number 2, for each of H and screw dislocation, cite the relationship between direction of applied stress and the direction of dislocation of line motion. Remember, you have 2 types of dislocation, screw dislocation and H dislocation. So what will be the direction of dislocation line motion in terms of the direction of the shear stress? What will be the location? Is it parallel or is it perpendicular? And then question number 2, what is the relation between dislocation motion and mechanical behavior of metals? So when there is a dislocation motion, what will happen to the mechanical properties in terms of strength, in terms of toughness? What will happen? Dislocation of motion, what will happen? Think and answer. And question number 2, 3, how the grain boundary can act as a barrier to the dislocation motion. So you have grain boundaries, right? So why do they say that grain boundaries can act as a barrier to dislocation motion? Why? What is the science behind it? Okay, just the tips. Different orientation, different plane, angles. Okay, think and answer. Okay, let's look at the answer. Okay, the question number 1 asks you on provide 3 types of strengthening mechanism in metals. Okay, there are 3 types. The first one is grain size reduction, smaller grain size. So if you have smaller grain size, you have more networks of grain boundaries. Okay, that's the tips for question number 2, 3. Another strengthening mechanism is solid solution alloying, where you add impurities, solid, into the atoms of alloy. Okay, smaller the impurity size, more better because it can fill the voids of the atom or the spaces between two atoms. And the third strengthening mechanism is cold working, where you purposely deform the atom mechanically, plastic deform the material mechanically so that it is in strain state. There will be no any further dislocation. So that is what we mean by cold working, which is strain hardening. Okay, so this is the types of strengthening mechanism. Now question number 2. For each H and screw dislocation, what is the relationship between the direction and also the direction of the dislocation line? For H dislocation, the direction of dislocation line is parallel. For screw dislocation, the direction of dislocation line is perpendicular. All this you can view in lecture 3. Okay. Now the next question. What is the relation between dislocation motion and the mechanical behavior of metals? Now you should know that the ability of metal to deform plastically depends on the dislocation, right? When an atom is being dislocated, that is where plastic deformation occurs. So the ability to deform plastically depends on the ability to dislocation to move. Now, the mechanical strength and hardness of a metal may be enhanced by enhancing the resistance to plastic deformation. If you resist plastic deformation, the mechanical and hardness can be enhanced. Hardness and strength are related to the ease with which plastic deformation can be made to occur. This is the keyword. Hardness and strength are related to the ease in which plastic deformation can made to occur. So if you make a material hard to deform plastically, your hardness is increased. Okay, by reducing the mobility of dislocation, the mechanical strength can be enhanced. That is, the greater mechanical forces are required to initiate plastic deformation. So if you have high hardness and high strength, you need more energy, you need more shear to initiate plastic deformation. Eventually, plastic deformation will take place for any material. That's the law. Provided that the force given to shear is greater than the holding energy. Okay. And by that, restricting or hindering dislocation motion renders a material harder and stronger. So your job is to make sure that the material don't have any dislocation to move for you to have plastic deformation. That is the science, that is the theory behind strain hardening. You move it and then you make sure that it doesn't move further. Plastic deformation, strain hardening, cold working. Okay. Next one, how grain boundary can act as a barrier to dislocation motion. Okay, so grain boundaries are since the two adjacent grains are of different orientation. The keywords that I'm looking for is different orientation. So if you have grain boundaries, two grains are in different orientation. A dislocation passing from one grain into another will have to change its direction of motion. Am I right? It's moving in this direction. Suddenly you have grain boundaries. It needs to move in this direction. You can look this in lecture 3. So it need to move the orientation. So it will have tough time. The atomic disorder within the grain boundary region will result in discontinuity of Schlipp's plane from one grain to another. So it is like losing its rail track. Okay, the train is moving according to the rail track. If there is a different orientation on the rail track, it stops moving. You don't have the guide to move along. So plastic deformation move in that manner. Okay, you need to have a clear path of atoms in right orientation. If you have a slight different orientation, it means that there is a gain boundary. Okay. Okay. Please take note of it. You can refer to the lecture notes. Let's look at question number 3. Describe solid solution strengthening. Okay, describe solid solution strengthening, which is alloying. So what is the mechanism of solid solution strengthening? Try to answer now. Try to answer now. Okay. Now let's look at the answer. All right, solid solution strengthening is a method of increasing a metal strength. Okay, how are you going to increase it? You can increase it by adding one or more elements, alloying elements. Okay, and if you add more alloying elements, you are actually filling the voids between the host atom. By filling the voids between host atom, you are creating a stress, a localized stress. Remember what they call that, tension, and also tensile stress, and also strain. Okay, you have tension as also compression. So by doing this, dislocation movement is impeded due to the lattice disorientation and the introduction of different bonding structures. These are the keywords. Highlight this. Highlight these guys. You can look into lecture 3, dislocation, solid solution strengthening. It impedes atom. The impurity atom distorts the lattice and generates stress. In your slide 24, small impurities, larger impurities, tensile strain or compressive strain. Right? Take a look at that. Here, I'll show you the answer here. Here you go. Okay, small impurities, large impurities. Large impurities create compression. Small impurities create tension. Okay. Tensile, compressive. Okay, guys. So in your test and final assessment, if I have asked this kind of question in detailed explanation, you need to come up with a very detailed explanation on it. Okay, you need to come up with a very detailed explanation. So the marks will be given according to the detailedness of your answer. Because all of these are open-ended books, so you can look at the lecture notes and so on, but marks will be given on the detailedness of your answer. Of course, the answer is correct. So marks will be given on the detailedness of the answer. Okay. All right. Let's look at the next question here. Question number 4. Okay, two previously undeformed cylindrical specimen of an alloy are to be strain hardened. Okay, strain hardening, cold working, by reducing their cross-sectional areas. So reducing the cross-sectional areas, cold working, while maintaining their circular cross-sections. For one specimen, the initial and deformed radiuses are 15 mm and 12 mm respectively. The second specimen, with an initial radius of 15 mm, must have the same deformed hardness as the first specimen. Compute the second specimen radius after deformation. So use the formula cold working formula. Yeah, use this formula. Find percentage of cold working or the first specimen, and then find the final diameter for the second specimen. Compute the second specimen radius. Okay, first you need to find the percentage of cold working and then find the diameter. Try to do now. Try to do now. I'll give you 5 minutes. Okay. Now let's look at the answer. All right. So the question I've given you, the initial and deform radiuses for the first cold working process, which is 15 and 12. And then for the second cold working process, use the same process, but they want you to find the second specimen radius with the initial radius of 11. So over here, two previously undeformed cylindrical specimen of an alloy. Okay, for one specimen, the initial and deformed radiuses are 15 and 12. The second specimen, initial radius is 11. What is the final deformation radius? Okay, it has the same deform hardness. So same deform hardness means same cold working percentage. Okay, percentage of cold working, area of AO initial minus final divided by initial times it 100. Pi r initial, use this formula. The initial radius is 15 over here. The deform radius is 12, which is this 12. Chip in your values in the formula to get the cold working percentage, which is 36%. Okay, you need to reuse the 36% because they said that it must have the same deform hardness. So 36 with 36 cold working percentage. Your initial for the second specimen, the initial is 11. 11 minus this is the one that you want to find, radius of the final deformed specimen, RD square over 11 times it 100. Okay, do the mathematical problem. We got 0.68, which is the radius. Right, and then you have the radius as 8.80. Right. Okay, guys. Try to do it. Now let's look at the next question. Question number 5. Provide two energies involved in the solidification transformation of pure metal. So this is today's lesson, okay, this week's lesson. So what are the energies involved in the solidification transformation of a pure metal? And also 5.2, 5 part 2, write the equation for the total free energy change involved in the transformation of liquid to produce a strain-free spherical solid nucleus. Assume homogeneous nucleation. So what is the total free energy equation? Write down the equation. Try now. Sorry. Try now. Try now, guys. Okay, let's look at the answer. This is the answer. So two energies involved are surface free energy, which is GS, and volume free energy, which is GB, bulk. Okay, this energy, this both energy contributed to the total free energy, which is GT. The magnitude of GS and also the magnitude of GB. So therefore, total free energy, volume of free energy plus speed, surface free energy. So sphere volume free energy is 4 over 3 pi r square, pi r cube, and the rate of change of GV plus width. For your what they call that surface free energy is pi r square and gamma, which is your surface free energy level. Okay, write it down. Okay, 4 over 3 pi r cube, change of GV plus width, 4 pi r square, specific energy level, gamma. Okay. Next question. Now, relate the degree of undercooling to the mechanical properties of metal. Justify your answer. Remember guys, I told you about the undercooling. Now, relate those with the properties, mechanical properties of a metal. What is the influence of undercooling to the mechanical properties of a metal? Justify your answer. So try to think. Try to think. What is the influence of undercooling for the mechanical property? Does severe undercooling increases the mechanical properties or compromise the mechanical properties? Think about quenching, guys. Quenching temperature. Okay. What would be your answer? Okay, let's look at it. Actually, the answer is the larger the degree of undercooling, the stronger the metal, the stronger the harder the metal. Remember, guys, about the critical radius. The more severe undercooling, the smaller the critical radius, the smaller the activation energy required. So high undercooling results in more nucleation sites. So if you have more nucleation sites, that will result in fine grain sizes, lots of grains, lots of sizes, smaller sizes. Therefore, you have lots of grain boundaries. Finer grain equals to large grain boundary area. So if you have more grain boundary area, plastic deformation won't happen that easy. So more hindrance to dislocation movement. See guys, this is how you relate it logically. That's what I'm emphasizing on logical thinking. If you're stuck with some question, relax, don't panic. Think of a logical sequence, how it will happen and what will be the results be. Okay. I think that's about it for tutorial. Where's the tutorial? Over here. Okay, that's about it for tutorial, guys. Any questions? Any questions? Clear, right? Okay, good. All right. Now, let's stop the recording.